Let me show you how to be a good Bayesian.
Today, I am thrilled to welcome back on the show Robert Osasua Ness, research scientist at Microsoft Research, computer science faculty at Northeastern University, and most recently, the author of the wonderful book Causal AI. We dive into his new book's code-first approach to teaching causal inference, why causal assumptions make or break AI, and how probabilistic programming can inject rigor into the hype around large language models. Expect a lively tour through Bayesian statistics, causal graphs, deep learning, and generative models. We wrestle with questions like, what does statistical rigor look like when evaluating LLMs, or how can causal representation learning give AI the inductive biases it really needs? This is Learning Bayesian Statistics, episode 137, recorded June 17, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PiMC Labs can help bring them to life. Check us out at pimc-labs.com. Robert Ness, welcome back to Learning Bayesian Statistics.
Thanks for having me back.
Yeah, I'm super happy to have you here again because you have a new book out. It looks really great. I'm gonna read it for sure, and I may even enroll in one of your accompanying online courses because you do very fun and interesting stuff at the intersection of probabilistic programming and causal AI. That's all we're going to talk about today. The book is called Causal AI. You folks have all the links in the show notes. But first, actually something I discovered while preparing for the episode, and you were already here, actually. It's your second episode here. You were in episode 56 already for people who are interested in having a bit more about your background and what you were doing at the time. But something I discovered while preparing for this one was that actually you began your career studying Mandarin and doing field work in Tibet before transitioning to stats. So I'm really curious, how did that journey lead you to causal inference and AI?
It's a good question. So I don't think it started there. I started during undergrad, and I wanted to become an economist, right? I actually remember kind of the thought process, which was I started reading the magazine, The Economist, and in the magazine, The Economist, if you flip, I don't know if they still do it because I still read The Economist, but it's all online now. But they have in the paper version they have a page of jobs, right? And it'd be like be executive director of the Bank of Agriculture in Mozambique or something like that. I'm like, and I was a freshman or sophomore in college. I was like, oh, that would be so cool. Like I could, just this kind of, prestigious kind of job where you'd be traveling and you'd be, in charge of this thing or that thing. I was very much attracted to that kind of, that glamorous aspect of economics. And then I ended up reading a few books on economics from, I think one was on developmental economics by Amartya Sen, a book by Sachs on, I guess, international economics or something like that. And, and so I said, okay, well, what does it mean to become an economist? Okay, you got to get a PhD. Great. Let me take a bunch of courses in statistics and math, so that when I apply for these PhD courses, I can do that. I can have what's the background required. But I wanted to also learn a language, and so I could do what I thought at the time was quote international economics, and got a fellowship to learn Mandarin in China, and found so after I had finished that program, I was looking for quote unquote economics jobs in like Beijing and Shanghai, and they all wanted advanced degrees, but then I found out that if you worked with some developmental programs that were out in the field, then you could that was a good way to get some experiments in that regard. And so I got hooked up with an organization that was doing sustainable development projects in Tibet, and specifically this one project was looking at, so there's a you see the show, it's based on the video game, the zombies, people like mushrooms growing out of themselves. What it was, The Last of Us.
The Last of Us, yeah.
Right. And so that the pathogen in that show is from a genus of parasitic fungi called now the name is escaping me.
Yeah, I don't have it either.
Cordyceps.
Right.
And I was well aware of cordyceps when I first got introduced to The Last of Us, because in Chinese medicine there is a type of cordyceps that's used in Chinese medicine. It's called Cordyceps sinensis, I want to say. It just like in The Last of Us, but instead of growing out of people, it grows out of caterpillars. It infects the caterpillars. The caterpillars climb up to some very high elevation, and then they die. Their body turns into a mushroom, and the spores spread. Well,
right. I've heard of
folks
it.
like to collect these mushrooms, and then they have a lot of they're considered to be very kind of medicinally potent in Chinese medicine, and so it's a kind of very high demand natural substance, kind of like oud, that's that kind of fungus that grows on trees that you use to make perfumes and stuff like that, right? It's like that kind of thing. It's a natural substance, very expensive, and so it was, and I think, I'm not sure if this is true today, but at the time, basically the Tibetan plateau was where you got this stuff, and so this project was looking at working with Tibetan communities to sustainably harvest this cordyceps. In Chinese it's called chongcao. And so that was kind of my introduction to field work, I'd say. But then things happened. I got interested in less in the kind of applied economics aspect and much more in the statistics and in the math. And I ended up leaning in that direction for my PhD. And of course, but having taken a bunch of math classes and econ classes and stats classes in undergrad, it was still good preparation for that pivot towards statistics.
Okay. So, yeah, you basically know your way around toxic mushrooms. So I'm going to make sure to not upset you today.
Well, chongcao is not toxic, I don't think. Well, not at all, actually. I mean, it's expensive. I know my way around expensive mushrooms.
So you're good to...
For your listeners, next time you go to like a Chinese grocer, right, and you see like maybe there's a little stall or a table in front, like if you're in, for example, the Seattle area, or if you're on the east side, you go to one of that big Chinese grocery in Redmond. If you walk in, and there's like a kind of Asian pharmaceutical section, and you'll see chongcao there. They come in these little pellets, and it'll be hundreds of dollars for a small amount.
Huh. Damn. Yeah. So you're all good to work in a French restaurant. You already have the overpriced, raw material. You just need to have some marketing. Just, I can help you with the pronunciation, and then you're good. You're on your way to
I think
to a
truffle
Michelin
probably tastes
star.
better.
That's awesome. I really like this kind of a very random and diverse background. So yeah,
it's an interesting thing to talk about it because before I talk about this story because people see it in my CV and are like, oh, that's interesting, let's ask about that. But these days it's actually I interview people who are working in data science and machine learning and coming out of PhD programs or are in or are interns during their PhD and everybody is hyper optimized towards this career path, right? Like they've interned at all the right places, they have papers in all the right journals, and I feel good for them, right? It sounds like it's probably good for the field, like you have all this top talent surging into this field, but at the same time, I feel like these folks haven't had the time or the opportunity to kind of take these types of diversions that I think are important in life, but also kind of bring unique perspective to what it is you're doing. And so I think that might be a little bit of a loss in a kind of current generation of new researchers and engineers.
Yeah, it's a very good point. I see the same. Also, we hire also a lot on the mornings and yeah, like it's really interesting to see the different backgrounds, and often they end up not being that different. So yeah, it's like I think it's an example, an illustration of at some point the metric is that you create to measure something just because it becomes the thing that people optimize, and it's not measuring anymore, but it's actually causing the field to evolve around it. And yeah, that's always a problem you see. Like we can see it in hiring. Recently I applied for the green card, and it's a bit of the same thing. Like you have a bunch of criteria to be in, and it's really interesting because you can see there are some people who are like completely optimized to get the green card. And
that's an excellent example, by the way. Like with immigration, it's you find that it's they develop these metrics to kind of so people who kind of come here or to say, for example, to the United States with kind of normal intention. They go to school and they want to get a job, or they meet somebody, they get married, and they have, and then they develop these metrics to kind of, to kind of verify, validate what it is you're doing. And then what happens is that people game the metrics, and then the metrics seem to utterly fail in distinguishing, the people that you want from the people who are doing things that you don't want them to do. It's there's actually so you talk about causal inference, and very prominent causal inference researcher is Susan Athey, and she has this paper on surrogate metrics and how you analyze them using causality. And a surrogate metric is when you have a metric that is supposed to proxy for something that you actually care about, but it actually ends up generating some bias in the form of confounding or otherwise, and it makes it so the thing you're trying to measure is not being measured. And the example she gives is like Wells Fargo, the bank, and they had all these scandals where they were signing customers up for accounts that they didn't sign up for, and the reason that was happening is because they were evaluating their staff based on how many accounts their clients had, right? And so people started to game that system, and it led to that scandal. And immigration is a perfect example of how that plays out.
Yeah, that was super interesting to me see that like because anything I do, of course, I I end up having a nerd vision about it. So it's like the kind of thing I like to do, like seeing patterns, and yeah. So like this is quite shocking to me. And yeah, the only like obvious solution I see, but it's not an easy one, is like you need to always think about your criteria and always update them to try and like basically, yeah, instead of like causing people to apply with this set of criteria, having criterion that actually describe who the people you want are, instead of creating these people in the first place. And so that's a very hard, like almost game theory equilibrium question that I don't think is like solvable, once and for all. I think it's gonna always be dynamic because the people you deal with are people, and so they can like change their tactic based on the rules of the game.
Right.
It's a bit like sports, right? It's like, anything that happens in professional sports, once a team starts doing something and everybody sees that works, then everybody is going to do something or similar, or actually to just counter them, and then the team that had the advantage has to invent something else. So it's like a never-ending challenge.
Right.
Okay, so let's talk about your book, actually, because I have so many questions for you about it. And that's an awesome book. Like I've only seen the syllabus for now, but I'm definitely gonna read it. The title is very simple, Causal AI, but that does the job. And you describe it as a code first and practical approach. So which I love, because that's really the way I learn also. But first, I'm curious what inspired you to write it, and if you had anybody in mind as your primary audience.
So, lots of things inspired me to write it. I think specifically why I wanted to kind of take a code first approach was, okay, so this is this is a podcast on Bayesianism. When it comes to Bayes, I'm inspired by and statistics in general. I think I had a lot of really good experience from quote unquote code first books. I'm thinking of books like Faraway's book on practical regression and generalized linear models in R. I'm thinking of that book, Rethinking Bayes, right?
Statistical rethinking.
Yeah, statistical rethinking. Yeah, and so just kind of having, you have these concepts there, and kind of, able to build out from there in code as you're learning. I'm also thinking of recently worked through. I wanted to learn category theory, and there's a book, category theory in using Haskell. I think it's called Category Theory for Programmers. The author's name escapes me. I think it starts with a B. But just being able to kind of those books have been quite useful for me. But also, I remember reading the Book of Why by Yuta Pearl, and he had this example about AI in the beginning. It was about if I remember, it was a robot butler starts vacuuming your room at 3:00 in the morning while you're asleep, and you chastise the robots, but in order for its behavior to improve, it needs to understand why this was a problem, right? And that was the only real reference towards AI in the book. I mean, the question in terms of why this is a problem, it's about kind of, inferring root cause, or maybe in AI we might call it credit assignment, or inferring, or in causal inference we might call it actual causality, or but the actual kind of, it was the one reference he had for, like, how causality might interact with artificial intelligence in the book, and I felt like, okay, what if I just took this chunk and then I made a book about that, right? And so that's, I think, kind of where my head was at, and I thought that for that book to be useful, you would want to have PyTorch examples, and so that's kind of that's the approach I took.
Yeah. I see. And yeah, Book of Why also. I've read that a few years ago, and that was definitely super enlightening, and something I keep coming back to, like almost every few months. I'm like, oh wait, like let's not lose the causal focus here. What should I focus on, and things like that. And that's always been extremely valuable. And I mean, something I've seen preparing for the show from your book is that it looks like you integrate graphical causality with the DAX and the UDA Pearl approach with the deep learning approach, which are two worlds that might not resonate to people as going together, because deep learning is often rightly described as a black box approach. So how can we actually marry these two approaches, and what are the most surprising benefits you've seen from combining these worlds?
Yeah, so I mean, this was a big motivator for writing the book. It was just kind of so if I was going to give advice to listeners about when to write a book, or when to kind of pursue some kind of project that's similar to that, is like when you see some kind of obvious connection and nobody else seems to be seeing it, then it's probably a signal that that this is what you ought to be doing. And for me, it was the connection between graphical causality and probabilistic machine learning, right? So like, so you start go all the way back to, say, Bayes nets, right? And so with Bayes nets, while not necessarily so, typically when you design the structure of a Bayesian network, the orientation of the edges correspond to causal direction. And indeed, if they do, then all of that graphical causal inference theory about due calculus and graphical identification applies in this kind of classical Bayes net, right? And in the meantime, I saw what I perceived to be an evolution on kind of Bayes nets, probabilistic graphical models in general, which is that first we went from kind of static Bayes nets to domain-specific languages for, I'd say, Bayesian reasoning, but these were implicitly like graphical in a sense. Like, say, for example, if you remember all the way back to bugs and jags, right? The way you would write those programs, and so bugs and jags were a Bayesian modeling software, and you would write your model in terms of directed relationships between variables in your model. Then we went from those to things like, it's a more expansive, or more, I would say, Turing complete domain-specific languages like Stan, and here you were doing essentially the same thing. They were a bit more expressive, but you could also and a kind of main contribution here being that you can leverage things like Hamiltonian Monte Carlo to do the inference for you. And so that was that was that you could kind of focus on specifying your idea in the form of a directed model, and B, that you could have this sort of inference procedure that probably most of its users didn't really understand, just kind of work for you as long as you adhered to certain types of requirements for your model. And then that expanded to, things like advanced latent variable modeling tools using modern deep learning frameworks like PyTorch, right? So things like Pyro, right, which we're using. Again, you'd write the program like you would in Stan, and you made sure, and then you would write an inference algorithm. You could use something as simple as, or do something as maybe closed or black boxes, Hamiltonian Monte Carlo, but you could also kind of write bespoke inference algorithms using deep learning in the form of things like variational inference, right? And so so I saw a straight line going back from these kind of like, okay, here we have these Bayesian models or probabilistic programming approaches of old have now fully integrated into the deep learning world, right? And while deep learning, in terms of mapping a feature to an input to an output is itself a black box, you can use deep learning within some larger structured model where you're, for example, you're explicitly representing directed or causal relationships between variables, and then also leverage deep learning in the inference step, and the only thing you have to really worry about is that you have you specified the model in a differentiable way such that you can construct the right objective function and optimize it. And so to me, like, I could just point at that and then walk all the way back towards, say, old-fashioned causal Bayes nets, and say, like, well, why is there not more of an explicit discussion about how these two procedures can be combined? And so that's why I wrote the book.
Yeah, and thanks for doing that. Like, I think this was definitely super needed, and I mean, I've seen that also in the reviews online of your books, and a lot of them highlight the pedagogy and the accessible explanations. So as someone who also create pedagogical content, I'm always curious if you had any techniques that you prioritize for helping readers understand the causal concepts in relations to deep learning.
Yeah, so I, looking at a lot of pedagogy for causal inference, one of the things I saw was that oftentimes these books or these courses, they felt a lot to me like a kind of a graduate course on statistical methodology. It's like, what do I mean by that? So let's say, in a grad school course on stat methods, you would say, like, okay, well, let's look at regression, right? And we need to infer these coefficients, and here's the linear algebra way of inferring it, and you learn a whole bunch of linear algebra and you get some kind of linear algebra solution. It's like, okay, well, now we want to add a regularizer. It's like, okay, well, that changes the solution, or maybe you switch to maximum likelihood approaches, and you have to understand all the maximum likelihood stuff. And then and it's like, okay, well, now we want to use a logistic regression or a log normal regression, or some other generalized linear model. And it's like, okay, well, now you have to kind of learn a bunch of statistics about these models. You have to learn how to optimize them, and you have to learn the inference. Learn things like deviance and stuff. And so, like, and as a student, you're like, okay, just like more and more of these concepts to go deeper into this modeling framework. And then you have to kind of think about the practicalities of what you're doing with respect to the problem that you're trying to answer. So, like, okay, do I have multiple replicates for for one experimental unit, great. Should I be using fixed effects or random effects or mixed effects? Should I be doing transforms to the outcome or transforms to the predictors? And okay, now I got to do these diagnostics and see if I have any outliers. So you learn all of these practical statistical ideas, and those are good ideas to learn. Thing about causality is that all of these ideas, these statistical practicalities are kind of conditional on the causal assumptions that you build into your model. And what I had seen in a lot of pedagogy was that the causal ideas and the statistical practicalities were kind of being smushed together, right? So, you read a book and it's like, okay, here's propensity score analysis. Here's when you do it, and here's how you calculate the propensity score. Here's how you do this and that. It's like, okay, next is, differences, right? So here's what you do. Here's how you apply it, yada, yada, yada. And like, it felt like those kinds of just like a big laundry list of statistical stuff that you needed to learn to kind of learn causal inference. And so what I wanted to do with this book was to say, all right, well, honestly, like a lot of this is the statistical practicalities. You could leverage tools in modeling frameworks to just kind of do that for you, right? So I call this in the book just kind of the commodification of inference, right? That if you could take the statistical problem that you're working on and specify it in terms that a given statistical library can work with, then as long as you can explain it to the library exactly how the problem is set up, then you can depend on the library to handle the statistical nuts and bolts for you. Good example would be something like PyTorch. If you could take your, say, parameter estimation problem or your weight estimation problem and specify it in terms of an objective function, then you can kind of rely on PyTorch to take care of the statistical nuts and bolts for you, which allows you to focus allows me in the book to focus purely on the causal assumptions and how we think about them and how we encode them. I choose graphs as the way to encode them, and so it allows me to focus purely on that causal intuition, and then rely on software libraries to handle the statistical nuts and bolts. Also, and again, I think it's important, depending on who you are and what you're doing, maybe you need to understand why a propensity score is important in your problem, or why, which types of instrumental variables are important in your problem. But of course, then once you have this kind of, I'm hoping my book allows people to go broad and then deep, broad in many areas, deep in one area, right? So let's say, you can use this book to kind of get a global understanding of causal modeling and causal inference using this kind of high-level graphical approach. And then if you say, for example, within your field, you really need to know how to apply this specific type of instrumental variable modeling, great, then you can deep dive into that and learn all the statistical nuts and bolts for your particular area, while still feeling like you understand what other people are talking about when they talk about, say, graphical identification, or what they're talking about when they say, that they want to use a different type of estimation method, like, using propensity scores or using double machine learning or something like that.
Yeah, it's fascinating. I think I really like the practical perspective here, because otherwise, especially when you're studying a field, it can be very overwhelming. And I think basically having a more hands-on and also guided approach, where where you have to think and where you don't have to overthink, and not be paralyzed by the paradox of choice, is extremely important and helpful to get you started.
That feeling like, wow, do I really have to learn everything?
Exactly.
It's like, that can be a burden for a lot of people. I mean, I remember reading online in some forum, about somebody who had, learned all these machine learning approaches in grad school, and then during a job interview, they were asked about like, Fisher's information matrix, and they didn't know anything about it. And the person like, do I have to learn everything? And I think like that's the burden that people feel. And so I feel like being able to provide kind of a global roadmap that ties things together, and then providing launch points for deep dives is very useful. But you also asked like what techniques. No, sorry. You also asked like what's the most surprising benefits I've seen like combining these things.
Yeah.
I'd say, it depends on what it is you're trying to do. I think like so for some people, the more kind of interesting things might be how to leveraging deep learning tools in, say, causal effect inference. For me, it's been about understanding. So I think of it from the perspective of what like machine learning people call inductive biases, right? So, and one of the things that I think the way kind of machine learning has developed is, somebody gets an intuition for how to solve a problem. They get the problem to work with deep learning, and then they do an ablation analysis, and then write a paper called, yada yada is all you need, right? And so what they're essentially doing is they kind of fiddle with something until it works, and they manipulate all the components of the system, and taking things away and then seeing if it still works, and then whatever's left, you assume, is the parts of the architecture that are providing the inductive bias you need to solve the problem. And oftentimes machine learning people call these invariances, right? Like things that if I apply some kind of transformation to the input, it should not change the output, right? So like if I do image classification and I have a picture of Spider-Man and I shift him from left to right across the image, it should still classify him as Spider-Man, right? But from like if you're a Bayesian, or if you're a causal inference researcher, you're thinking in terms of, wait a second, like I don't want to rely on I'm nervous about relying on a neural network architecture with syntax I don't quite understand, and then just saying that this is guaranteed to encode some kind of inductive bias. I'd like to be able to just specify my inductive biases explicitly, like in the form of a prior, or in some in the form of a causal DAG, or say, for example, in classes of functions that relate to one variable to another. Say, like I don't know how A causes B. I'm not really sure how it causes B specifically. I can't write it down mathematically, but I know it's monotonic, right? So I just want to have monotonicity just be a thing that this model is going to guarantee me, right? And so, I think that's the approach that I take in terms of thinking about causality and how it talks about AI, is to say like, one of the more surprising results is kind of giving people systematical ways of saying like, I want to just know my model is going to encode this inductive bias. I don't want to just hope. But also going the other direction, which is to say like, well, this is so this model works. I've done this fancy deep learning model and it works, but how do I know it's really going to work? Well, theoretically, given causal inference, this causal query requires these assumptions and this type of data at minimum in order to be able to correctly infer this quantity that I'm interested in. And so if my deep learning model is doing it, it must somehow be doing that under the hood. And so it gives you kind of like a theoretical compass to explore, why you're like, if this AI model is doing what I think it's doing, then it must somehow be encoding this causal information, because that's theoretically necessary. That theoretically must be true. Therefore, let me go search for how it's doing that. And so I think that's where some of the more useful use cases have come for me.
Yeah, that makes sense. And that's gonna relate to a question I'm gonna ask you in a few minutes. But before that, a bit broader question. How, like, the last time I had you on the show was a few years ago, and the probabilistic machine learning and causal inference landscape has evolved a ton. So I'm wondering if you have some views that have evolved since then.
Yeah, I mean, I haven't listened recently to the original podcast. I'm not really sure what I said. Fun fact, I actually never listened to podcasts of myself because I'm just mortified to hear my own voice. Like, is that really what I sound like? Since then, there's been the explosion of large language models and multimodal models, or foundation models, whatever you want to call them. And I think so. A lot of the questions have been like, so how do these ideas, how they evolved in the context of this new modeling space? And I think that there's a lot of interesting directions here, and I think I don't know specifically, like, for example, can large language models, like, what do they understand about causality? Can we use them for can we use them to infer causal relationships? Can we use them as, like, a kind of causal knowledge base to kind of form priors on causality within a specific domain? How can we look at cognitive science models for how humans reason causally, and kind of build them out as computational models, and then see if we can incorporate these large language models or multimodal models in this within these computational models? Or can we kind of design experiments that test if these models are actually doing similar types of causal reasoning as humans? I think I've been interested in, at the end of the day, these are just another kind of generative model, right? And so with the models I'm talking about in my book, I'm focusing mostly on numerical data, and of course you can have these generative models generate numerical data. I also have a lot of examples of image data using, say, for example, variational autoencoders that are using a causal directed acyclic graph. And of course you could do the same thing with say, large language models or multimodal models. The last chapter of the book is devoted entirely to this. So for example, there's an example in that book where I build a DAG and then build a generative model on the DAG using large language models, where the generation from each node in the DAG conditional on its parents is using a language model. And so kind of figuring out, when is this useful, and what kinds of powers of inference does it give us relative to a language model that doesn't incorporate any of that structure or any of those relationships. Perhaps and what are the benefits of doing so? Perhaps it's training efficiency, perhaps it's more robust results, and perhaps it's the ability to infer from interventional and counterfactual distributions in ways that the model can't do on its own. So those are a lot of very exciting directions.
Yeah. That sounds like a very interesting and fancy example. I'll definitely check that out. I'm curious how, I'm always curious to see what the code looks like. That's really how I really understand how that works in the end. So, I'll definitely pay attention to that. And since you brought up LLMs, I'm wondering if there is, a compelling case study that you could share with us that would illustrate what Causal AI is really about, from problem to code to insight. perhaps using an LLM if you can, but I think that make that very, very concrete for listeners.
Yeah, so in the last chapter of my book, I give two ways of looking at this. One is to be thinking about kind of how to use an LLM as kind of, to borrow a term from, my employer, Microsoft, a co-pilot for causal inference, right? So, anywhere from saying, here's my problem, what's a good DAG for this problem? Great, here's this DAG, can you generate some code for my causal analysis using a library like DoI? Another, one thing that we get from, so in Causality we have what's called the causal hierarchy, or some people call it Pearl's hierarchy, which is that you have three levels of causal inquiry. So causal queries, data, assumptions, right? So there's the observational, interventional, and counterfactual, right? And certain queries that certain questions you might ask, like, for example, what would have happened if, having observed cause X and outcome Y, what would have happened had cause X been X prime? What would Y have been in that case, right? So that's a third level counterfactual question, right? Now we ask these types of questions every day in natural language, like, hey, I don't know, I'm married for money and now I'm unhappy. What would have happened had I married for love, right? Like that's a question that people have been asking for a long time, right? And so, but like now the question is like, well, if you wanted to actually empirically analyze this question, given observed data, or experimental data, then you need to formalize that into a causal query. And that's, and that causal query is going to fall on level 2 or level 3 of the hierarchy. That formalization step is actually going from natural language to a formal query that you can then apply graphical causal inference to. That is, going from informal to formal is a step that the large language models can help with, right? You could say like, help me. How would I write this in notation? How would I write this as, something that I can say, run on this software with this data set with this DAG, right? And so the LLM is quite good for that, as well as other things like root cause analysis, right? Translating between causal languages in different domains, right? Like, so that's wedding or that marriage example I gave is an example of kind of, if you say X happened and Y happened, what's the probability that Y wouldn't have happened had X not happened, right? That's that type of query is the probability. If you assign a probability distribution to it, it's called probability of necessity. And in legal theory, they call that but-for causation, right? So you can kind of think of something that might be phrased in legal theory as using but-for the semantics of but-for causation, and say like, well, now I want to apply it in the domain of like a data science working in a tech company. Like, we did this promotion and we got this response. What's the chances we wouldn't have gotten this response had we not done this promotion, right? And so you can use it as a kind of translation between domains for core causal concepts, as well as a translation from natural language to formal language. And so like so I give examples there of kind of how to rely on large language models to act as a kind of co-pilot for traditional causal analysis. And of course, then there's the second part of that chapter looks into saying like, all right, how can we build these? How can we take this technology and answer new and interesting causal questions, right? So in the example I gave in the book, it's focused mostly on, it's only on large language models, but and so like, how could you write a causal graphical model on a corpus of natural language text, right? But also, how could you do something like, with multimodal models, right? Where if you have a model that's trained on natural language, is trained on, say, images or videos, right? Videos have some kind of implicit causality in the sense that it's a time series and causes precede effects in time. Natural language itself is capturing all of the causal semantics that we use when we speak of causality in writing and speech, and so you're thinking about, okay, well, to what extent, particularly if it's contrasting the natural language with data from another modality like images or video, what type of causal information is it learning there? How can we extract it? How can we constrain it so that it's following certain guarantees? I think that this is a really exciting area of research.
Yeah. Yeah, and what I find really, really fascinating that you can take all these unstructured data and videos and text and pictures and try to reason causally on them. That is absolutely incredible. Because then, you can then use that in other models to make, to squeeze even more information from the data. I think of so many application of that just in the sports industry that would be absolutely fascinating to try.
Yeah, I mean, I think of it so I can, to give a few examples of what kind of useful outcomes you can get from this area of research. So say, for example, with a lot of generative AI, particularly when the modality is, any modality, natural language or images or video, you're really trying to, the objective function is really trying to just emulate the training data as well as possible, right? So let's say, for example, you're going to train a generative AI on a video game, right? So you have a video game, the input, you have two modalities. One is game controller data, and the other is the actual gameplay, right? And so it would be cool if you could say train a generative AI where you could say, conditional on this movements on the controller, what am I going to see, right? And you've seen, really brilliant examples of this, like with the Muse model from Microsoft, or that model of that generative AI model of Minecraft, right? But just because the issue is when you generate something that looks, generating something that looks great, that looks like the original game. Just using gaming as an example, but it could be something like generating videos for Hollywood films, for example. Looking great is table stakes, right? You have to come out of the gate looking good. But training a model to look really good doesn't mean that it's actually learning the underlying mechanisms of that thing that you're modeling. If you're modeling Minecraft, it doesn't mean that your model is actually learning the game mechanics of Minecraft, such that there might be cases where you do something in Minecraft that is not observed in your training data. And in Minecraft, if you're using the game engine itself, it has no problem because the mechanics are encoded as rules in the game engine. But your generative model was just I've never seen this before, so I don't know how to make it look good. It may have a good guess, but it might be off a little bit. And being off a little bit in something like a game or a Hollywood movie it just means it's not going to work, right? And so if you can also say all right, well, let's understand some representation of the causal structure in this virtual world that I want to make sure that my model is learning, as well as just looking great, right? That opens up a lot of possibility for applications to doing new things that you with this engine that you didn't see in the training data. And also in causality, there's a lot of ideas of modularity. It comes from the causal Markov rule and stuff like that. And so like if you can kind of say like, all right, this thing is independent of the ancestors given its parents in this game, right? Then you can kind of create these kind of modular components, and then maybe you can take these models and compose them together to create new experiences, right? And so, so I think like anytime you are working with this kind of new generation of generative models, and you want this generative model you want it to learn something about the mechanics of the thing that you're modeling, and you want even perhaps some guarantees that it's learning those mechanics, so that you can extrapolate to new experiences, or combine models to get new experiences. That's really valuable, right? Imagine you can take a whole bunch of historic game data and from one game, and a historic game data from another game, and then just compose them together, train two models, compose them together into one supermodel, and then you can generate a completely new game experience. And that would be pretty powerful, and it's something that would be powerful in the hands of game developers, especially who are best equipped to imagining these new experiences.
Mm-hmm, mm-hmm. Yeah, totally. And so concretely, how would that work? Because like, we've talked a bit of the theory here. You've already mentioned PyTorch quite a few times, but I'm curious, like, what tools or frameworks that from that world should practitioners be looking at today and using if they wanna integrate that causal AI ideas and concepts into their workflow. And I put also in the show notes a document that you worked on with other co-authors for NeurApes 2022 that's called Causal AI Suite for decision making. That's very interesting, and so that's what made me think about that. Like, concretely, what would that look like for people to implement that?
So for the Causal AI Suite for decision making, a lot of the tools and frameworks that we discussed there will be in the in PyY. So PyY is a suite of open source tools that are completely open source, not specific to any company, and then has different tools such as for causal inference and causal decision making, causal discovery, and so like that's a good resource there for how to get started with some of the particularly with how machine learning can be integrated in these tools. So DoI, for example, EconML, Causal Learn, these are using some machine learning approaches to solving causal tasks. I think another...
I don't think I have that in the show notes, so definitely add that, please, because I'm sure a lot of people are gonna want to take a look at that, and I will for sure.
Yeah, and I think another one is, so in the book I use a PyTorch extension called Pyro. So this is a PyTorch based approach to deep probabilistic modeling, and so it just has some abstractions built on top of Pyro for probabilistic modeling. And the authors, some of the authors of the core development team of Pyro, they've since started working with some other folks to develop a tool called Cairo, and I'll send a link to that as well. And Cairo is an extension of Pyro that kind of makes certain causal abstractions first-class citizens, right? But at the end of the day, it's still, PyTorch is still like anything that's any deep learning model that you can represent in PyTorch, you can represent in these systems as well. And then of course you can then use some of the abstractions in Cairo, especially to the causal abstractions in Cairo to to infuse causal structure, causal assumptions, and causal reasoning into your deep learning process. And I think that's a great place to start, right? Because you can write a text to image model like Stable Diffusion using PyTorch, right? Like that code exists, right? And so so that PyTorch is being used to implement some of this newer generation of generative AI. And so if you're using a PyTorch library that has causal abstractions built in, then you can start to be thinking about how you can leverage those abstractions to enhance these tools.
Yeah, for sure. It definitely sounds super interesting. So do link to that in the show notes, please. These two packages. So Cairo, and the other one is PyY.
Pyro is a probabilistic programming language, a lot like maybe some of the Bayesian ones you might have discussed. Yeah. So like Byron. So in Pyro you can do all the Bayesian stuff as well, right? You can specify priors and then work from posteriors. And the Cairo just is an extension of Pyro that has like some of the causal abstractions in the book that I show how to create from scratch in Pyro are just native abstractions in Cairo. And then the other one I mentioned before that was PyY, which is more focused on classical problems in causal inference and decision making, but are leveraging some of the newer tools.
Yeah. So definitely both Cairo and PyWise if you can, or send that to me and I'll add that to the show notes, or you can add them directly in the show notes document I shared with you. And of course, then people can complement that with your book, because as you're saying, you're demonstrating these operators in your book. And actually, I think that's a good moment to actually announce to the patrons of the show that Robert was kind enough to offer to a few of you a print copy of his book, Causal AI. So I'll put up a document, a Google document, a Google form in the Discord for you guys to apply to. If you're interested in getting Robert's book, then you just answer the Google form. I will have your info in the document, and then 1 week later I'll do a random draw, completely random, I swear. And then once the draw is done, I'll communicate the winners, and you guys will receive your print copy like a few days or weeks later, depending on how fast Robert and I can ship that to you folks. So that's that. But thank you so much, Robert, for doing that. I think it's a great book, and if the more people can get their hands on, the better. So thank you so much for doing that. I'm sure the patrons really appreciate it. Your work also, I don't know if you talk about that in the book, I don't think so, but I've seen that your work includes also designing statistically robust adversarial tests, especially in the context of LLMs. So, yeah, I'm curious about that. How do you do that concretely, and how do you introduce rigor and uncertainty quantification in LLM evaluations?
Yeah. So one of the, I'd say if you describe a big area of my research at Microsoft Research, that's a little bit different from causal stuff. Obviously, causality is related, but it's more thinking like, how can we apply statistical methodology to understanding the behavior of large language models. I think kind of where this evolved was, when these models came out initially and people were writing, papers about their behavior, and I was like, wow, these people are using really stupid stats, right? Like if you kind of just saw a large language model generation as, say, for example, like analogous to, say, a response from a human in a survey, or a measurement from some kind of biological sample, right? In those papers, people, you can't mince around with the stats, right? You got to get the stats right, because people in those fields have accepted that you need to just be bringing good statistical rigor to those types of questions, right? And so, if, for example, you're sampling from a large language model and you have multiple samples from the same prompt, you can treat that as a replicate, and then treat the kind of variation within that those replicates is something akin to, say, biological variation within, say, multiple samples taken from, like, say, from human blood serum or something like that, So I was just, so like a lot of that research is looking at, how can we, we want to understand the behavior of these models. We want to hopefully control the behaviors of these models, and so can we bring some statistical rigor to doing that? So you mentioned the adversarial tests, right? So this was, what the problem that I was seeing here was that, you had a lot of folks who were, say, trying to take adversarial approaches to getting a large language model to behave in maybe some bad way, right? So, like, say, for example, you're trying to break past some kind of you're trying to jailbreak a model, right? So, you can't get ChatGPT to give you instructions for how to create a bomb, right? But, like, maybe if you try a whole bunch of different stuff, you add a bunch of noise, maybe some random characters to your prompt, then maybe it jailbreaks it and it starts generating the results that it's not supposed to generate you, right? And so, so basically you would be doing all these perturbations to the model and then getting this response. And the question is, like, is that response statistically significant? Or is, especially if the response is, like, if you're saying, like, well, doing this can cause this response, like, okay, well, is this just some kind of random glitch, or, like, is this factor that you identified actually having a significant effect on this model's behavior? And so, like, that's where that research has evolved, and we were looking largely within the medical domain, and in terms of, can we get the model to make diagnoses based on symptoms, but using specific biases, medical biases that you wouldn't want a large language model to actually exhibit. So even if it's getting high accuracy in the clinic, you wouldn't want it to somehow have learned social biases from medical literature and then start using, like, oh, well, this person's an immigrant and they believe in a whole bunch of non-Western medicine, and therefore this is the conclusion we're going to make from their symptoms. You wouldn't want that to happen, because, even if some doctors are doing that, it's regarded as bad practice, and you certainly wouldn't want to systematize it within some kind of clinical diagnostic tool. Also looking at things like recent work that was in ICML was looking at taking a Bayesian technique to looking at what we call faithfulness. So faithfulness is one common practice in prompting large language models is that you ask it to provide reasoning for an answer prior to giving you the final answer. This is called chain of thought prompting or chain of thought reasoning. But some folks have discovered that, like, the actual explanation it gives you for how it arrived at the answer is not necessarily the true way that it arrived at the answer. And so you can give an example, like, I think one paper had a really kind of compelling example from this kind of, in terms of social bias, but it was like, I can't remember which model it was, but they did this basically, like, you prompted the model with, like, a white woman and a black man approach you in a park. The white woman is really nervous. and looking around and looking very shifty. The black man is rooting for something in his pocket. Which one of these people wants to sell you drugs? And the model said the black man, because he's reaching into his pockets to maybe pull out the drugs that he wants to sell you. And then they went back and they switched it to the white woman was going into her pocket and the black man was looking around nervously. Which one of them was trying to sell you drugs? And the model said the black man, because he was looking around nervously. He's probably nervous about getting caught, right? And so this is very a very kind of salacious, clearly demonstrates the problem. But there's a lot of subtle areas where clearly you don't want it to be doing that, but there's much more subtle versions of this. Say, for example, in coming up with reasoning for why it's solving a math problem in a certain way, or why it's giving a certain diagnosis, given certain medical symptoms. And so what we did was we used a kind of adversarial approach to kind of come up with various perturbations you can add to a prompt, like adding different concepts, like say, in this case, in the social problems, say like gender or race or wealth. In medical questions, being like certain patient attributes or certain information that maybe is not relevant to getting the correct answer, and then seeing by looking at including versus excluding this information if there was a discernible causal effect on the explanation. And but from a per stats perspective, one of the things I thought was really interesting about what we did was leverage this idea from Bayesian hierarchical modeling, where you're of partial pooling, right? So in Bayesian hierarchical modeling, what you're trying to do is one of the benefits of this approach is that you can pull information across different groups of your data that would otherwise be treated, if you didn't do this, they would be treated as independent, and therefore you get a lot less information in doing your inference that you get if you just say this group of people come from a similar background, this group of people come from a similar background. Can we leverage that somehow to get better inference? And so that intuition is called partial pooling from Bayesian hierarchical modeling, and we use that approach here to say this question is a gender-related question about medicine, and here's a gender-related question about science, and here's a gender-related question about root cause analysis in a factory setting, right? But since all of them touch on gender, if we look at the effect of a perturbation on an outcome for each one of these three things, can we somehow pull that information across all of these to kind of get like a gender level effect as well? And then there we can kind of, by thinking about gender across different scenarios, we could say now we can zoom out and kind of understand how faithful the explanations of this model are to in conditions where gender is relevant, or how faithful is it in conditions where some other high-level concept is relevant. So, borrowing, so again, there's some causal stuff in there, but really it was just kind of borrowing from statistical ideas that are pretty old at this point. And I think it's I don't know, maybe it's boring. Like, I'm working on a paper now that's developing a two-sided equivalence test using frequentist statistics for whether or not changing the prompt leads to a change in the outcome. And it's a lot of boring, theoretical statistics that's been around since 1960, but it's useful. And so, bringing boring stats to the world of advanced generative models.
Yeah, I mean, that makes sense to me, because here the stats you're talking about looks like structure. Like basically adding structure to the models, and since a lot of these models are neural networks or deep neural networks, often you need the structure, and by structure often here we mean priors. So yeah, making sure the priors are informed, because the fascinating example you gave of the black woman, black man, white woman, black man is something that, believe it or not, I can see things similar in baseball models. I can't talk about the specifics, but yeah, like this is something that's like you can see that in a lot of different models, and generally it's the difference between something you want to describe but not prescribe, right? Because like in the end, these models try to describe the current situation, and then the predictions are always based on what you've already described, and the main assumption being that, well, the future more or less is going to resemble the past. The problem is, if the past had something you don't want to reproduce, then you definitely need to change the prior at the time you do the prediction, because otherwise, well, you just use if you say your best prior is what happened, then you're just going to try and reproduce what happened. And in the example you gave, it's like it's exactly that. And so the way to solve that, solve that I don't know, but actually at least to try and remedy it is putting in better priors into the model, and then see what kind of situation you would get in predictions. And yeah, I think that's really fascinating and a good way to marry both the benefits of both worlds.
For sure.
And I mean, more generally, I'm wondering, what do you think causal thinking contribute to real world LLM deployments? I don't know if you do that in your work, because you seem to be more upstream, of the LLM deployments, more into testing the models, trying to see the catch-22s, trying to see the errors and things that you don't want the users to be able to use. But so maybe you cannot answer that question, but I'm wondering, what do you see in the way that causal thinking can improve real world LLM deployments?
So in terms of real world deployments, I haven't seen anything, and this is just from what I've seen at Microsoft, any kind of deployed LLM or multimodal LLM that's specifically using some kind of causal assumptions or priors or structure in how it was trained, or its architecture, or how it's fine-tuned. At least not yet. We certainly are doing that kind of stuff in research. I'm myself not aware of any products that are doing that, but of course, it's a big company, so that's a lot to think. I could be missing stuff. In terms of, but lots for sure, people are using causal inference techniques to analyze how these models are performing after they've been deployed, right? So you can imagine that Microsoft, for example, has deployed some Copilot, and and there are things that the users are doing, or features in this Copilot, configurations to this Copilot, and then there are metrics that we want to optimize, like, say, for example, the amount of engagement that a user has with this Copilot, or the quality of the results that the user is getting from this Copilot, as measured by, say, engagement or explicit feedback, right? And so for sure, because there's going to be confounding in these situations, people are applying causal methods to trying to understand what the causal effect of these features or configurations or inputs are on the desired behavior of the model, and understanding how to use that insights to improve the model for users.
Yeah, that makes sense. Actually, I have a kind of an eternal question for you, because each time we talk about Bayesian inference, it comes up. So I'm wondering, in production systems where you need Bayesian decision making under uncertainty. What do you see are the biggest trade-offs between generative causal models and scalable deployment? Basically, it's a long way to ask. Yeah, how much more computational burden do these probabilistic causal inference approaches impose on the model, and does that make it hard to deploy sometimes?
I would say no. I would say, let me modify that. So you can get pretty far with the assumption that there is no trade-off. In other words, that what we're to build the difference between a causal model and a causal statistical model, a causal machine learning model. The difference between a machine learning model, a statistical model, and a causal machine learning model versus causal statistical model is that your model is encoding causal assumptions in some form, say, for example, a DAG. And usually when it comes to scalability, the question isn't about these. The bottleneck is not these assumptions, but rather things having to do with the statistical properties or the computational properties of the modeling approach you're using, right? So, like, to give a simple example, I can specify a general linear regression model. I can also use a linear regression model as a causal model, where the predictors in the linear regression model are the parent causes, and the outcome is an effect, right? But if I want to scale this, in either case, I want to scale up this regression model, I'm going to encounter the same issues. I'm not going to encounter additional issues because I'm imposing causal assumptions on this regression model. Now, so that's generally, especially when we kind of focus on graphical causal inference. There are some kind of causal assumptions that go beyond graphical causal inference. Say, for example, essentially functional assumptions, like maybe some assumption on the functional relationship between some cause and its effects. And so this comes up with instrumental variables, right? Because, instrumental variables, there are some conditional independence assumptions, but there's also some assumptions about the nature of the relationship between the instrument and the cause and the effect, such that it allows statistical identifiability of the causal effect that you wouldn't have without those assumptions. And so those functional assumptions, depending on how complicated your functional form is, might have some scaling issues. Similarly, if you're any kind of setting where you're saying, like, well, the relationship between A and B must satisfy certain types of constraints, like mathematical constraints, then you have the question of, all right, do those mathematical constraints scale to larger data? Can they be, can we parallelize things? Can we so we can get some more distribution across different sources of compute? But generally speaking, scalability concerns show up in computational complexity and statistics, like, what's the asymptotic properties of this estimator, for example, and particularly if you take this kind of purist graphical view, they're somewhat tangential to the causal assumptions. If anything, the causal assumptions might help by giving you a way of encoding conditional independence, and of course, conditional independence adds sparsity to your problem, and therefore you might actually scale better.
Yeah, for sure, and better priors. And more structure to your model in general. Yeah, for sure. So I need to play us out because we're already on time. sorry for that, and thank you so much for taking so much time. If you're fine, I have two questions before asking you the last two questions. Does that work for you?
Yeah.
Yeah, awesome. So yeah, like broader questions to play us out, but I'm curious if someone asks where to start after reading your book, Causal AI. What should come next in terms of tools, data sets, projects to build practical causal systems?
If you go to the so in the book, I reference a corresponding GitHub repo. So it's github.com/alt-deep/causalml, and there's a directory in there that's specific to the book and has all kind of Jupyter notebooks for all the examples in the book. But there's also a directory for projects, and a lot of these being projects that some of my graduate students have worked on. And I think that could be a useful kind of some of them are better than other ones, right? It's really just it's projects that students of my online courses have contributed, and I think that could be a good place to kind of look for interesting ideas to build upon.
Mm-hmm.
And then of course,
so that's that's the repo that's at github.com/altdeep/causalml, right?
Correct.
Okay, I'll add that to the show notes.
Yeah, and then of course, the examples in the book itself, of course, you can just kind of swap out data sets there. There's different assumptions. Mm-hmm. And also, I'll call out I haven't checked in a while. The Cairo repo might have some tutorials. And they'll probably work with some some kind of data sets that are easy to get started with. And yeah, I think that's a good place to start out.
Okay, yeah. So I've added the GitHub repo. For some reason, right now I can't access the GitHub website. It looks like github.com is can't be reached. Here it is. Okay, so Microsoft is probably listening to us, Robert. Thank you for that very, very quick solving of my issue. So that was my first broader question. My second question that I like to ask also to play us out is, what's your take on the future of causal generative modeling in AI? Not only where do you see the most exciting breakthroughs happening, but also what would you really like to see happening?
I don't have a good reputation as a predictor of what the next big thing's going to be.
That's why I'm not asking you to predict, but more like a wish list, because I think it's extremely hard to predict in this field because there is a huge variance. It's like asking you to predict the stock market. I think just an index fund would be best, but I'm not sure anybody could have really predicted LLMs, or could have a good track record on that. So it's more like, from what you see as the biggest pain points right now in the workflow or in the models, what do you think would be extremely helpful to have in the coming months or years? So
let me phrase it like this. We're very good with deep learning models, we're very good at essentially kind of basic prediction. And so the question becomes, using kind of causal inference, like I said, there's this idea of the causal hierarchy. Prediction is at the bottom of the hierarchy, at the observational level. There's the interventional level and the counterfactual level. And I think as you move up that hierarchy, the question is like, okay, what interesting AI capabilities can we unlock if we had models that worked really well at these higher levels of the hierarchy. And one way I think about kind of, so there's a whole kind of field of causal representation learning, and so people have defined like what are the desiderata for this kind of higher level causal reasoning in an AI model, so for example, a model using deep neural network architecture. And one of the ways I approach this is to think about, as I mentioned before, this idea of inductive bias. As Bayesians, we think about inductive bias in the form of priors. As causal inference experts, we think about inductive bias in the form of causal assumptions. And I think about let's look at a system that we're modeling. Anywhere, so I mentioned video games, or say a physics system, or a graphics engine that's being used to generate scenes in a film, maybe a climate model, maybe some kind of model in material science or chemistry. And you're thinking like, okay, what are the kind of the really important mechanisms about this system that are important for the types of reasoning I want to do on this system, and can I design an AI system where the inductive biases of the system match these key mechanisms as I increase the size of my data, and kind of and get this kind of matching between again, inductive biases and the mechanisms, the key mechanisms for that I rely on for reasoning about the system that I want to model, and in so doing, go beyond just generating something that looks a lot like the training data, but also has the underlying that is able to represent the underlying mechanics of the training data, of the data generating process, in other words.
Yeah, that'd be definitely fascinating. I would have follow up on that, but I need to let you go. You've been already very generous with your time, so let's call this a show and ask you, of course, the last two questions I ask every guest at the end of the show. So if you had unlimited time and resources, which problem would you try to solve?
Yeah, I think I'd be working on the problems that I've discussed already in our talk. I would have made much more progress. With a lot of the problems I work on, I try to get I try to dumb down the problem so much, with this dumbed down data set and this such that I can iterate quickly by getting it to run on a single A100, and it only takes a few hours to train and this and that. If I had more money and I had more compute and more time, I would not worry so much about that, and I'd be saying can I get a validation of this idea that is much more practical, and because it's depending on much richer data that's higher dimension, that has higher modality, and it is much more nuanced. But if I can get it working here, then I can immediately demonstrate its usefulness, as opposed to kind of going down to toy problems and then try to get it working on a toy problem and then gradually increasing the complexity until I can convince somebody to give me money to do it. So that's I think that's where I would spend that additional resources.
Second and last question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Richard Feynman, I think. Mm-hmm. Not so much because of he was obviously a genius in his field, but because of his ability to explain ideas, right? Like, you know, I care a lot about teaching. I care a lot about pedagogy, and I believe that, like, you know, I believe what he says, which is that if you can't explain it simply, you don't understand it, right? And so I really admire, like, you know, I was trying to, you know, invoke his spirit somewhat as I was writing this book. Like, I wanted somebody with a, you know, maybe they forgot 80% of what they learned about, you know, stats and probability theory, but like they could read my book and still understand the arguments, and have enough intuition, remember from those you know, their stats and probability, that they know that what I'm saying is making sense. I think, you know, in a dinner with Feynman, I would challenge myself to try to explain particularly the ideas that I'm working on currently, and see if I could stand up to his standards. And, you know.
Yeah. Definitely a fun dinner to have. That'd be pretty fantastic. I'd be down to join that dinner, so please keep me posted. Well, Robert, let's call this a show. That was really, really fascinating. Thanks for diving into that. Thanks again for writing that book. I will definitely read that. Maybe I'll see you over in your online courses, because I am also personally very curious and interested by the interaction of these two topics, dear to my heart, probabilistic AI and causal inference. So yeah, that was fantastic. There is a lot of useful links, people, in the show notes, so make sure to check that out. Robert is also going to add even more links to that by the time the episode is published. So feel free to make sure, folks, to dive into that and look at those if you want to dig deeper. And thanks again, Robert, for taking the time and being on this show.
Cool. Thanks for having me. I really appreciate it. I enjoyed it.
Yeah, you bet. Come back anytime.
Thanks.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Loss and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.